Let's look at several examples of determining whether a given matrix is diagonalizable, and if so, we're going to find a matrix P and D such that our matrix equals P, D, P inverse. In particular, D is going to be a diagonal matrix. So in the last video, we defined when this would be the case. So we said that a matrix is going to be diagonalizable, specifically when we can find a basis for the right size space. In this case, it would be R2, since A is a 2 by 2 matrix. So if we can find a basis for R2 consisting of eigenvectors of A, then A is diagonalizable. And we looked at the setup for P and D. So kind of the first step here is to find eigenvalues and eigenvectors. Again, we've gone through all the sort of algebraic steps of how that works in a previous video. And in fact, in this video, we're going to be looking at the exact same examples that we have looked at in previous videos where we were focusing just on eigenvalues and eigenvectors. Now we're going to kind of apply those to this idea of being diagonalizable. So I'm not going to go through any of the algebraic steps. I will use Sage, and I'll show you that in our book to kind of find the eigenvalues and eigenvectors, which is again something we've seen in the previous video, but just as a reminder. So we've got this matrix, negative 2, 6, negative 2, 5. We're going to look at first for eigenvalues and eigenvectors. So again, let's jump to our book. In our book, you can find these Sage cells, which we've talked about before, that allow us to perform different matrix operations in Sage. And in particular, we've got a setup here, and I'm going to put our first example of a matrix in this spot here, where we can then compute the eigenvectors. This is in section 4.2, specifically activity 4.2.5 includes kind of the particular Sage instructions, although again, this is really just the syntax. So a reminder of the syntax, you do not have to pull up Sage in our book or in this particular section. You can type this into any place where you can run Sage and it will work. But I thought this would be the easiest to do. So let's go ahead and run this. Okay, and we can see our eigenvectors, our eigenvalues to begin with. So our eigenvalues are 2 and 1, and our eigenvectors corresponding to each of those, 1 2/3 and 1 1/2. Any scalar multiple of these vectors will also be eigenvectors. So I might scale these just to avoid having to use fractions. So we've got, let's go back to our slides here and we can put this information in. So we've got the eigenvectors and eigenvalues. Okay, so we've got, let's see, lambda. Maybe we'll do it like this. Okay, so E sub 2 is going to be the span of, again, it was 1 2/3, but let me scale that up so we can get rid of the fractions. So 3, 2, and E sub 1 is going to be the span of 2, 1. Okay, so we've got two distinct eigenvalues that guarantees that their eigenvectors are going to be linearly independent and therefore form a basis for R2. And so A is diagonalizable, And in particular, P is going to be the matrix whose first column is 3, 2, whose second column is 2, 1, and D is going to be the diagonal matrix where we put those eigenvalues down the diagonal, so 2, 0, 0, 1. And I'm not going to show this here, but you could try this on your own, that A would equal P, D, D inverse. Let's go to the next example. So we've got our next matrix here, negative 1, negative 1, 1, negative 3. Let's again go to Sage, and we'll put that matrix in and run it. And here we can see that we've got just a single eigenvalue, -2, and the only eigenvector that pops up is 1, 1. So this tells us that we do not have we're not going to have enough eigenvectors to form a basis for R2 because we just have the one linearly independent eigenvector here. If we wanted to look at the characteristic polynomial, just so we could see kind of what would happen here. Remember, this would have a factor of lambda plus 2, and it would have multiplicity 2. It would be lambda plus 2 quantity squared, right? So that's an indication that we have this repeated eigenvalue, which doesn't necessarily mean that our matrix is not diagonalizable, but when we come down here and see that the only eigenvector that comes up here is 1, 1, and we don't have two linearly independent eigenvectors corresponding to that eigenvalue, that is our indication that A is not diagonalizable. So if we come over here, again, we'd have just the one eigenvalue, -2. E sub -2 is the span of 1, 1. And so A is not diagonalizable because we do not have enough linearly independent eigenvectors to form a basis for R2. And that's where we will, sort of end a question like this, because if it's not diagonalizable, then, there's no use in trying to construct this P and D matrix. We're not going to be able to. Next example, one more 2 by 2 example, 1, -2, 1, -1. Let's once again jump back here. Put that one in. Okay. All right. So this one sort of looks a little bit crazy what popped up, but we could see this capital I, this -1 times capital I as one of our eigenvalues. That is an indication that we've got a complex eigenvalue. And so if we are open to looking at, complex eigenvalues and eigenvectors, we do actually have distinct eigenvalues, and therefore, we could form this basis. So if we were working with complex numbers, which I'm not going to do in this video, but we will kind of come back to this. If we were working with complex numbers, then we would be able to construct a this PDP inverse where P and D would both include complex numbers. So maybe that would be interesting on its own if we were comfortable with that case and we were working with complex numbers, then we could do that. We're going to actually see a relationship in this class between complex number eigenvalues and eigenvectors and some trig functions. So more to come on this, but for now, let's just kind of come back here and we're just going to say that our eigenvalues are complex. So more on this later. Okay, and we'll just go on from here. All right, let's go to the next example, a 3 by 3 matrix. And again, let's jump back here and we're going to put this 3 by 3 matrix in and run that. Okay, and so we have three distinct eigenvalues, 3, 1, and -1, each with an eigenvector. And we've talked about how in this case we will have these eigenvectors are going to be linearly independent, and so we will have this matrix being diagonalizable. Okay, and so we found here. Maybe I'll just jump right to writing out P and D. So A is diagonalizable because we have these three distinct eigenvalues. So let's go, P is going to be 0, 1, 1, and then 1, 1, 2, and then 1, -1, -1. No need to scale any of those. They were all whole numbers. You don't need to scale even if they're fractions, but I personally think it's a little bit nicer just to work with integer values if you can. And then our diagonal matrix here, we're going to put 3, and then 1, and then -1 down the diagonal. Okay. Again, making sure we sort of went in the same order. So the first column of P had to be an eigenvector that corresponds with the eigenvalue 3, and then so on and so forth. So we've got that. Let's try our next example, 3 by 3 matrix. And so let's, again, pull up our book here and put this matrix in. Okay, and so this matrix, we have two eigenvalues, -2 and 1, and this number 2 here tells us that 1 is a multiplicity 2 eigenvalue, but we only see one eigenvector here. And so this matrix would not be diagonalizable. So let's maybe write out the work here just to make it very clear. We have E sub -2 is the span of, let's just keep the fraction maybe, 1, 1, 1/2. And then E sub 1 is the span of 1, 1/2, -1. Okay. Again, we do not have enough. We would need 3 linearly independent eigenvectors here. So in order to have a basis of eigenvectors for R3, we do not have that. So in this case, A is not diagonalizable. And so far, we've had 2 examples. I'll come back here. 2 examples with repeated eigenvalues. This one for 2 by 2, this one for 3 by 3. And in both of those cases, A was not diagonalizable. So you might start to get the sense that that will always happen. That if you have a repeated eigenvalue, then your matrix is not going to be diagonalizable. That is not the case. Let's do this next example here. So in this example, let's go ahead and do that computation. So we've got our matrix in here. Okay, and so we could see here that we have 2 eigenvalues, 3 and 2, and the eigenvalue 2 is multiplicity 2, but we have 2 linearly independent eigenvectors to go with that eigenvalue. So the null space of A minus 2I is, dimension 2. It has, it's spanned by these 2 linearly independent vectors. And so we have enough linearly independent eigenvectors in total to span all of, to form a basis for R3. So if we write that out, we could have E sub 3 is multiplicity 1 and is going to equal the span of 1, 1, 1. And then E sub 2 is going to be the span of 1, 0, 0. And then maybe I'll scale this one by 2 to get rid of the fraction. So 0, 2, 1. So A is diagonalizable. And we could write P equals 1, 1, 1, 1, 0, 0, 0, 2, 1. And D would be 3, 2, and then you just repeat. You put another 2. So this is a nice example of a matrix that has a repeated eigenvalue that is diagonalizable. So it can happen. You just would need to check that the null space of A minus lambda I for that repeated eigenvalue is equal. The dimension is equal to the multiplicity of that eigenvalue. So it does work out sometimes. Okay, just to summarize this idea, to determine whether an n by n matrix is diagonalizable, we have to go through the following steps: find the eigenvalues, and then find the corresponding eigenvectors and eigenspaces. and then determine if there are n linearly independent eigenvectors to form a basis of Rn. We went through, both using the computer as well as doing it all by hand, each of these steps in previous videos. So, depending on the particular question or what you're using this for, you may have to do some or all of this by hand, or maybe some or all of this just using a computer. It kind of just depends on the particular request, but this is the process. And if you do have n linearly independent eigenvectors to form a basis of Rn, then you can form your matrices P, which is going to be V1 through Vn, whose columns are the eigenvectors of A, and then D is this diagonal matrix, lambda 1 through lambda n down the diagonal, with the associated eigenvalues. Okay, so hopefully this video gave you a good sense of how we can both determine if a matrix is diagonalizable, as well as writing these special matrices P and D when that is the case, when a matrix is diagonalizable. Still to look at in future videos are the cases of complex eigenvalues, right? We sort of brushed that off in this video, but I do want to explore that further. And then also, some more applications of this. Why is this property of being diagonalizable something that we even care about? So more to come on this in future videos.